stream as well. So, ever since the class where I lost my recordings, I have been simultaneously streaming to YouTube and recording to my local hard drive just in case there was a problem with either of the files. And a couple times recently, I noticed that for whatever reason, the file on YouTube actually ended prematurely, but the one that I captured locally had the whole class. And so I put up the one from Tuesday
Are you freezing?
and I noticed that the audio and the video are a little bit out of sync. And I don't know why, because that doesn't happen consistently. It only happens sometimes. So I apologize for that. If you're trying to watch the video, it's going to be a little bit weird because what I'm talking about is clearly not what's on the screen. So, in recognition of that potential complication, I'm going to try and do a better job of narrating where I am, saying what slide I'm on or what page I'm on of the handout. Listening to the video, then hopefully you can follow your own version if the video doesn't sync. I'm still trying to figure out why that would have been the case, but that's what I got for now. So it's an imperfect system, but hopefully the version that goes straight to YouTube seems to be better in terms of the timing. So I hope that that one is working, but we'll see. Let's see who else is here. We're getting a few more folks. Who did I miss? Kaylin's here. Hello. And Farhan is joining us. There we go. So I put up some new stuff for next week. We get to start lecture 5, and I built a brand new example. That's example 5A, and I've got example 5B. So two different examples using two different data sets. The idea behind these is getting to the point where we're fitting general linear models with more than one type of predictor at the same time. So what is known more conventionally as multiple linear regression. So those things are available for you. And in honor of Halloween, I thought I would show you a couple pictures that folks gave me a couple years ago with some of the scariest things in stats wise that you may see. So here's one of them. If you can see the screen, it is a pumpkin that someone carved p equals 0.06 into, the scariest thing they can think of, because it's just on the other side of significant. And another one which took way more work. Here's one. You can read this. It says inferring causation from correlation. The scariest stuff. So that one took a lot of work. That is a top-notch carving effort. So I like those. So hopefully I'll get a chance to show you pictures from Halloween with Huey on Tuesday. And if any of you want to share pictures from your Halloween, I'd be happy to see those as well. And in honor of putting up Lecture 5, I am happy to report that one of my favorite TV shows came back this week. The show This Is Us. Is anyone else a fan of the show? No, just me? Really? I thought you guys would have been my demographic for sure. So yeah, I love the show, and I'm going to use it to illustrate unique versus shared variance in predictors and regression. I'm going to use that as an example, so just wanted to put that out there. Too busy doing stats homework to watch TV. Touche, touche. I am a slave driver. It's true. But if Grey's Anatomy comes back, then I will be all set in terms of my entertainment because I am a diehard Grey's Anatomy fan. So can I get an amen on that one at least? Grey's Anatomy? Okay, a few more nods on that. Yeah. Yes, amen to Grey's. Although I really miss Christina Yang as my favorite character on there. I really wish she was still on there, but she's off doing fun things of her own. And now I have something yellow on here. Is someone drawing on my screen? Because I didn't even know that was a thing. We'll find out. Yeah, I have something yellow. Okay, no drawing on my screen while I'm talking. That's not fair. I don't know where that came from. I'm going to stop the share and then see if it comes back. Because I didn't think I had the capability to draw in yellow or any other color for that matter, but maybe I do. All right, there's the beach again. So let me first ask, any questions about anything we want to go over before we dive into stuff? You have formative assessment number 4 to work on. That is available to you, and you should be able to answer the questions on that. But any questions on that or otherwise? No? Okay, then I want to start. Eeny, meeny, miny, mo. Let's go with lecture 4. There we go. And the idea of trying to test the model as a whole, whenever you have more than one slope in your model at the same time. We started talking about this last time. So I am on slide 13 of lecture 4, which is talking about sums of squares. So sums of squares is the numerator term in an equation for variance. So it's how far off something is from something else squared and summed across all the observations. What those somethings is determines what the purpose of the sums of squares is. So there are 3 different ones that we want to have access to in our results in talking about how to test more than one slope simultaneously. We have sums of squares model, sums of squares residual, and sums of squares total. So the idea of total is just all of the information that there is to be had in an outcome variable. That's our baseline. That's what would be given by the empty model. And then once we start adding predictors to the model, how much of that information has been captured or attributed to the predictors and how much of it is still remaining. So sums of squares model is the idea of information that has been captured by the predictor variables that you've given slopes. So the little equation here next to sums of squares model is y hat sub I. That stands for the predicted outcome for each person from the model. So whatever the regression line or the group variable lines say that your outcome should be, that's your y hat, minus the sample mean, which is what the predicted outcome would be in the empty model. So relative to just giving everybody the same predicted outcome, how much more information have your predictors introduced in terms of being able to differentiate the predicted outcomes across people? So we want high sums of squares model because that means our model is doing good to differentiate people. In judging how good the model did, though, we also want to know how many slopes it took to get to that level of information capture. And so that's what's known as degrees of freedom for the numerator, which is the number of fixed effects k minus 1. The minus 1 is because we don't count the intercept, because the intercept is in every model starting from the empty model. So the number of slopes. So how much information did the predictors capture per slope gets us over to this column, which is mean square model. So all of these things are going to be available to you on your output. This isn't something that you have to worry about being able to compute. So that we want to know then what's left over. So the idea of residual, you can think of that as synonymous with leftover. How much information do we not know why it's there? How much variability in the outcome remains? So after we put in our regression line, each person's value is still going to be off that line to some extent. How deviant are those values from what they're supposed to be? How much information is left unexplained, unaccounted for, unpredicted? And so that is y sub I, which is the real outcome that each case got, minus y hat sub I, which is the one that the model predicted. So how far off are you from what the model says you should have had for your outcome? That's what SS residual is getting at. And it also wants to know how far off per slope that you could have added. So that n minus k term, that's known as denominator degrees of freedom. And that has to do with how much could still capture, how many slopes could the model use to capture that remaining information? And that's a function of sample size minus the slopes you've already included. So if we have how much information is unpredicted divided by how many we add to capture that, we get to this mean square residual thing. And mean square residual has a special name. And I've already asked you for it in your homework at least 3 times. What's the synonym for mean square residual that you know? You can talk or you can chat. Your choice. I don't know that this one's a gesture though. Variance, need a modifier for the word variance. Starts with an R. ANOVA is a type of model, but the model would have, there we go, residual variance. Yeah, mean square residual is the same thing as residual variance. It is labeled mean square error in SAS, and it's labeled mean square residual in Stata. So error and residual are synonyms. They both represent the idea of unexplained information. There is residual variance in an analysis of variance. There's residual variance in a two-group t-test. There's residual variance in a linear regression. There's always residual variance because your model's never going to be perfect. So regardless of what kind of predictors you put in, so long as they don't perfectly predict the outcome, there's going to be variability in the outcome that is unexplained by those model predictors, and that unexplained variability is known as residual variance, which is the mean square residual term. So in terms of my Coles analogy, can I give that one to you again? Because I've worked out a more complete version of that. So the ultimate question that we would want to know is, did we get a good deal? Right? Phrasing it in terms of my mom, Marcy's question. Should she be proud of herself for the amount of clothing that she has amassed for only spending, say, $10 or whatever it was? So we got to know, how many things did she get, and how much money did it take to get those things? So like, how much stuff did you get, say, per dollar spent in your shopping bag? That's mean square model. To put that into the context, like, is that a good deal, or is that like a good deal in terms of Macy's, right? Because these are different price brackets. To be able to contextualize it, we would want to know, okay, so what would be the total amount of stuff left in the store that you didn't buy, and how much money would it have taken to buy all those things? Residual. So a good deal is when you got a lot of stuff for not a lot of money relative to what's left in the store and how much money it would have taken to empty the store. How's that? Eh, yeah, it's a bit of a stretch, but I'm trying. I'm trying. So
Can you repeat that, please?
yeah, so the idea here is that my analogy of, did we get a good deal at Kohl's, is like, do we have a good model? And in order to conceptualize that, what is a good deal? It's when you get a lot of stuff for not a lot of money. So, okay, that's like mean square model. How many dollars did we spend? That's degrees of freedom numerator. So if we have how much stuff did we get over how much money, it's sort of like stuff per. So then the other half of it is, so stuff per dollar is going to be need to be put into context. Like a good deal at Kohl's in terms of how much stuff per dollar is not going to be the same as a good deal, say, at Macy's or at Nordstrom's or someplace where the store prices are a lot more expensive and I never want to shop there. Because even if I could afford a $100 shirt, there's no such thing as a shirt that's worth $100. I'm sorry, there's just not. Like in my vocabulary, right? It's just unnecessary. So I can't go to Nordstrom's, and that analogy won't work there. But the rest of the store then is my comparison. So if I took into account how much stuff is how much stuff is left in the store, and how much money would it have taken to buy all that stuff? Then sort of stuff left over per dollar as a comparison to that, that's mean square residual. How much is left, and how much money would it have taken to buy all of that? If we have sort of left per dollar it would have taken, that's mean square residual. So a good deal is the same thing as a significant model. And just like we have for any slope significance test, but we also need an effect size. And so we end up with this mean square model divided by mean square residual is going to be a new test statistic called F. F is a ratio of what you know over what you don't know. each weighted by degrees of freedom it took to know it or left over. So F tells you the slopes that you've added in a per slope metric helped enough. And the effect size that goes along with this F is R square. So R square is a really important effect size for a model. It tells you, you can think of it two different ways. The proportion of residual variance that your model explained, so relative to the empty model that has all the variance in the outcome, by how much did you reduce that? By what proportion did you reduce it? So that's one. The other way you can think of R square is if you took the y hat column, so the first term in sums of squares model on slide 13 here, y hat for each case. Okay, what does the model say your outcome's supposed to be? Well, you've got the right answer. You've got the column for what the outcome actually is for each person. If you correlate those two columns, y hat with y, that correlation, that is R square. So if the predicted outcome from the model is significantly related to the actual outcome, then you have a significant model. So that's the new concept that we're working on right now. Rather than just testing each slope or any linear combination of slopes, how do they work together as a set to predict the outcome? And that is given to us by this type of table that we see in our output. Do you want to see an example? This type of table in the outputs? Sure, we've already seen them, but I've skipped over them because we hadn't needed them up to this point. But this is the three group example. So I am on example 4, starting at the top of page 4, and looking at the effect of 3 category respondent rated working class, low, middle, upper, and to go into the model. So both predictors coded 0 when I'm talking about the low group. The first predictor, L versus M, is coded 1 if I'm talking about the middle group. And the second predictor, L versus U, is coded 1 if I'm talking about the upper group. So that give me how the middle and upper groups, of course, differ from low, and the intercept is going to be the mean for the reference group. So what I want to know, in addition to each of these specific contrasts, each of the 3 specific group differences, is whether the slopes work together as a set to give me a significant amount of prediction. Did I get a good deal? Did these slopes account for enough information to be able to generate a predicted outcome that is correlated with the real one? So we have the code that we've talked about the last couple classes. And here's the table in SAS for these data that goes along with what I was just talking about. So this is page 4. So I've highlighted here in bold font the numbers that are going to show up in your homework, the things that I'm going to ask you about, because these are the things that would go into a real report of this analysis. We're going to want to have degrees. So degrees of freedom for the model, that is what's known as numerator degrees of freedom, and that is the number of slopes. So right now we've got 2 slopes, that's why it's 2. Degrees of freedom for the error term is otherwise known as degrees of freedom denominator, and that's n minus k. In this sample, there's 734 people. We estimated 3 fixed effects in this model. I've got an intercept and 2 slopes, and that's why it's 731. 733 is the total degrees of freedom after you factor in the fixed intercept. Sample mean at minimum to be able to do any of this. Sums of squares column, that's the amount of information in that line. The error is the amount of information left over. Once we weight these things by the degrees of freedom, so sums of squares for the model divided by degrees of freedom for the model gets us over to the mean square column. So that's information captured per slope. That's what mean square model gives you. Likewise, information